Part, a catalyst results in an increase in the rate of reaction by a factor of 10 at 100 degrees C. Okay, so we're into the Arrhenius equation, and we've got K2, the rate constant K2 is going to be 10 times the rate constant K1. We've got the temperature is equal to 100 degrees C. As soon as you see that, make the conversion to Kelvin, that's 373 Kelvin, because all your calculations are going to involve Kelvin, never Celsius. And what we've got to do is calculate the change in the activation energy. So we're going to want the activation energy for 2, perhaps that's going to look 2, let's put a 2 down there, and minus the activation energy for the initial E1. That's the value we're after. Okay, well, as I said, it's the Arrhenius equation. So we know that the rate constant is given by A times E to the minus EA over RT. In the practicals, we met the case where you had rate constants with different temperatures, and we derived an equation for dealing with that. In this case, we have to derive a slightly different equation. So what we've got then is we've got K1, it's going to be equal to that activation energy 1, and you've got K2, is equal to AE to the minus EA over RT, and that's activation energy 2. And what we'll do is we'll divide those two equations. So that will give us K1 over K2. The A's will cancel out. It's going to give me E to the minus EA1 over RT divided by E to the minus EA2 over RT. This is where you have to be a little careful to make sure you get the maths right. Right, what I can do is instead of writing the exponential, this is to a power, instead of writing it to a minus number and putting it in the denominator, I can move it up to the top. So that's the same as E to the minus EA1 over RT times, I'll bring this up to the top now, by changing the sign. Okay? And if I'm multiplying these together, then I can add them. So that's the same as E to the minus EA1 over RT plus EA2 over RT. Right, now what I'm going to do is take logs of both sides. So that'll give me the log of K1 over K2. And if I take the log of this, if I take the natural log, the exponential will just disappear and leave me with the power. So that's going to give me minus, I'll tell you what, let's take the RT out. So that's going to be RT out, and that will give me EA1 minus EA2. Again, just be a little careful with the signs. I know I'm doing a little bit of maths here. Just got to be a bit careful with the signs. Okay, well we know all the information we need now. We know this ratio K1 over K2. We know that K2 is 10 times K1. So this can be written as the log of 1/10. That's going to equal minus 1 over R, of course, is 8.314, times the temperature, which is 373, times, we've got that difference in EA. Now we're actually after that. Let's just write it. Let's just write it this way. So EA1 minus EA2. Okay. So bring this up here. Run out of space there. So I've got EA1 minus EA2 is going to be equal to log of 1/10 times 8.3 314 times 373. So all I've done is multiply both sides by this denominator. That's brought it up to this side. I've got a minus in there, I mustn't forget. The minus is going to go in there. When I work that out, this I can just put into my calculator now, and you're going to come up with a value of 7.14 kilojoules per mole. So the number you come up with is actually going to be 7,140. And I've turned it into kilojoules rather than into joules. Okay, so that's the amount that the activation energy decreases by. Any questions? Is there anything on that you want me to go over again?
How did you, I'm really confused how the EA1 minus EA2 went up there, like times inside.
Oh, here.
Yeah.
I just wrote it the other way around. So what I did was I took that side, I wrote it over here, and that's equal to this side. So I'll tell you what, let's do that in 2 steps then. Let's write that. So that's the log K1 over K2 is equal to minus 1 over RT times EA1 minus EA2. So what I did, I've just multiplied everything by RT. That would give me RT times the log K1 over K2 is equal to minus EA1 minus EA2. Can you see that is the same as that? I've just written it the other way around. Yeah, is that okay? I need a bigger board really. Okay, so that's 6A. Let's have a look at 6B. Use the following data to plot a graph. Okay, so let's have a look at this. So this is, we've got a table of break constants, we've got a table of temperatures. Notice the temperatures are in degrees Celsius. So you never do calculations or graphs in Celsius. You're always going to convert it into Kelvin. So that's the first thing you can look at. Use the following to plot a graph to determine the pre-exponential factor for the reaction. So break constants, temperatures, again, you're immediately thinking about the Arrhenius equation, which is this. And if you're going to be plotting a graph, you're going to want to put this in a form where you'll get a straight line. So to do that, you take the logarithms of it. So that's the log of k is equal to, when we take the log of this, well, this is a times that, so you first of all, you can add those, so it's going to be plus the log of a, I'm going to put that at the end. And then the log of this bit, well again it's an exponential. If I take the natural log of exponential, the exponential disappears, it just leaves me with that power. Now, if I plot on the y-axis my rate constant, and on the x-axis I'm going to plot 1 over t, then I'm going to have a straight line where the slope, n, is the activation energy over R, and the intercept, C, is going to be this pre-exponential factor, or the log of the pre-exponential factor. So that's what you're going to try and do. I'm not going to plot the graph here. What I would always do is write out the table. I'm going to do the log of the rate constant, and then I'm going to do 1 over the temperature in Kelvin. Plot your graph. On the x-axis you've got 1 over the temperature. I'm going to put Kelvin there again to remind you. I'm going to have the log of the rate constant there. You'll get a straight line